Hi folks, just quick if I'm going to look up at this optimization section, but basically it's to do with differentiation. So usually they give you a little problem, and so this one, for instance, is taking some kind of rectangle or whatever. Doesn't matter the material it's made out of. I'm sure it does for those who are manufacturing this. But we're taking this and 6 meter is 4 meters, and what we're going to do it? They're going to extract corners from it. So they're x by x. So each of the corners are going to be x squared. So that's why they're removing that. And once they remove the corners, they end up with other dimensions for the kind of the base area. So just to show you um, what the base area is, it's you can see it's probably 60 to the 2x and 40 to the 2x. So where do we get that actually base area coming from? So here, so 60 to the 2x, that originally came from the 6, but you were removing an x and an x, so that's where they get the 6 take away 2x. I hope that's kind of clear. Is it clear? And likewise, you had the 4 there, and you were removing an x from there and an x from there. So x, a wee x. So that's why you get 4 take away 2x from there. I can know you don't like all this algebra stuff. You just hate algebra. Why you doing maths? I don't understand that myself personally. Um, so I'll just move on from there. So that means once we've removed the corners, what we're going to do here is kind of fold up um, the sides here. So we're just going to join them up together. Do you understand what kind of, do you need a wee picture, a wee story, just to show you what's going on here? I think I'll give a wee story. Why not? Right, so what's happening here is the following. So we're just taking a wee a paper here, and what we're going to do is just like I showed you there. I'm going to take the corners away here, so I'm going to do it very nicely for you, because I can actually pause this video here for you. That's that's actually fantastic, Tommy. That's beautiful. So what I'm going to do there, so see with those corners, I'm going to remove them, right? And I'll just let you know that no children, animals, or adults were helping the process of this. So we're just extracting the corners here, and that, okay. So I'm just going to take this along a wee bit further because it takes ages, and I talk for ages. So let's see. Will it take us along? Yeah, yeah, they go. Taking us along. So we've got to the final corner. Oh, four, four, four corners. Four corners. Four candles. I'm just turning this off here because I'm very pernickety. Right, so that looks okay. So it looks like I've got a central base area and four external rectangles, and I'm going to use those four external rectangles. I'm going to fold them up. That's what it looks like I'm going to do here. So what's Tommy doing here? Tommy he's going to play a wee game here, right? What's he going to do? I know he's oh pick a card, any card. But if you pick one, it's going to be the same card, isn't it? What's the probability there? So what we're going to do now is we're going to take the external rectangles and just fold them up and make sides. So let's move this one a wee bit further. Let's move it on a wee bit further. Um, so you don't get totally bored. And just see how it goes. Because it's great, it's fantastic when I'm filming this. There you go. You know what a cuboid is? So that's what I'm talking about. I'm calling this a cuboid. I'm saying I'm folding this in a cuboid. Cuboid's a box. It's a box, but it's an open top box. And so there's four missing corners, and there's the resultant item. And that box, oh, it should be full of chips and mayonnaise and vinegar and stuff like that. Or a salad if you're vegetarian. Salad, well, like lettuce and tomato and whatever. So the dimensions here, what I'm just pointing out there, is it's 6 take away 2x from the top one because we're taking 2x away from each of the lengths. Yep, I'm taking x away from each of the lengths, so that's why it's 6 take away 2x. Okay, okay, see that 6 take away 2x, 4, and the 4 take away 2 lots of x's from there. That's where we're getting that from. Okay, can you see that? There's one other dimension that we need to mention here. So what's that going to be? That's going to be the height. And so I have to maneuver the little box here in order that I can insert that dimension there. So you can see it. So what's it going to be? We're going to show you it. That's it. So that's it. Can you see that corner there? We've removed that. So that's why that's height x. X to x equals 40 with 2. And it doesn't matter the order that these things are multiplied in because we have a length and a breadth and a height. So that's what we've actually got here. So I'm going to just go back to my whiteboard. So I'm coming back to here, and there you go. All that for that. All that for that. I should be doing Star Wars stuff like that. Right, so we got to there. So there you go. There's our dimensions. Multiply them out. You should be able to do that, folks. Not me. You. Multiply it out. Sort yourself out. Okay. So we're looking for a volume here, and they're talking about looking for a maximum and minimum volume. So see, whenever they're talking about max and min, they're talking about differentiation. So differentiation usually means dy by dx, but they're not talking about dy by dx because they're talking about v, and v is dependent on x in this problem here. So it's a change in v in relation to the change in x. So that's what they're talking about here. So the v by dx or v dash. V dash. That's what they're talking about here. Right. So the v by dx is equal to 0, and they're actually, they're putting something here that 0 x between 0 and 2. So why is that? We'll come back to that. Or will I explain it just now? What do you want? Do you want me to explain why x is between 0 and 2? No, I'm not going to explain that now. I'm going to let you think about that. Why x is between 0 and 2. It's something to do with those two constraints. Okay? That's why x should be between 0 and 2. So you think about that, clever people. Right, okay. So we've got an expression for the volume there. We can differentiate it. We know the rules of differentiating. I'm not going to explain how to differentiate a function. You should know that by now. Okay. So let's make that derivative that we got equal to 0. Yeah. And I'm looking at that. So that's a quadratic function because it's x squared. And I'm looking at the numbers 12, 40, 24. They're all divisible by 4. So let's divide them all by 4. Okay. So I'm now looking at it, and the first thing that comes into my head is, oh, can I factorize that? That's what I'm thinking. I'm thinking about it too long. If I'm thinking about it too long, it means no. So I can't factorize it instantaneously. So if that's not the case, then I could get involved with completing the square or something. But I think I would just use the quadratic formula. I think um, that's what I'm going to do. I think I'm just going to use the quadratic formula. Yep, there we go. And numbers in front there. Let's get the 3, the 10. What's going on here? So can you see what I'm talking about? The quadratic formula with the A, the B, and the C. is 3, B is -10, and C is 6. So that's, we're getting them all from there. Right, hopefully you can see that. But you're seeing that on so many occasions. Right, so we'll just move on. So we're just going to put these in the quadratic formula, file numbers in, 10 plus 5 plus root 7 over 3. Oh, where does he get that from? Right, just in case, for those who are interested, where did I get that from? Well, 10. I can see that these are all multiples of 2, so 10. That's 2 times 5 plus or minus the square root of 4 times 7 over 2 times 3. Okay, so what's happening here is, to get that next line, take out the square root of 4, and so I've got 2 times 5 plus or minus 2 root 7 over 2 root 3, and then what's happened, we can cancel out 2 everywhere, and hopefully have 5 plus or minus root 7 over 3. Doesn't matter, just you go and use your calculator and you will get both solutions. So that was just a wee reminder of how to tackle surds. Surds, how absurd are surds? So that's what I did there. Okay, so that's it. 5 minus and 5 plus. And then we just use approximate values there, 0.78 or 255. So we're just going to file them in the volume there. I'm actually going to test. I'm looking at the first derivative here and the second derivative here. I'm not using a nature table, and I'm putting in 0.78, and I must have went ahead earlier to put in 0.78. That's fine. So put 0.78 into my second derivative, and 24 times 0.78, well that's less than 0, so that's actually all I need to see here. 24x, well, when I put that in there, because that's less than 1, then the answer is less than 0. And when the answer is less than 0 for the second derivative test, less than 0 means negative, and when you're negative, you're no happy. So that's why it looks like that. It's no happy, is it? Not happy. So not happy means well, actually it looks like a maximum at the point. So we have actually found that it's a maximum at 0.78. So that's fine. So we've confirmed that. Right. And I'm going to change this. I'm going to change this. I know I put that in as 0.0.79, but it is 0.078. File that in, and it's 8.45 meters cubed. So I'm just going to, just for completeness here, here, and here. So I'm saying at 0.78, and file that in there. It was less than 0, so it was a maximum at 0.78. Right, so that was my arithmetic. Okay, so I'm kind of framing that. Right, so then I did stick in 0.78, and that came up, it yielded a volume of approximately 8.45 meters cubed from my wee box there. There you go. Perfect. I am happy with that. Okay. Right. So, can I eventually shut the door on this? Yes. That was only one example, folks. There, this optimization usually, not always, but for us, this topic, it will involve differentiation. So that's what we're going to stick with. So maybe do another one. Okay. Right. Bye for now. Bye.